Okay, so the Laplacian is a very regular operator, meaning in particular it's invariant under rotations, translations, and dilations. So let me talk about what each one of these means. So we're going to have a function, and we're going to assume that the Laplace of u is equal to 0. Okay, so if we say that something is invariant under translations, what does that mean? So invariant under translations. Okay, so a translation is a linear transformation that takes the point xy to the point x plus a, y plus b for two real numbers a and b. And so when I say that the Laplacian is invariant under translations, I mean if u satisfies the Laplace, and I define a new function, v of xy equals u of x plus a, y plus b, what I mean then is that the Laplacian of v is also equal to 0. Okay. And really, we can even say a little more than that. So let me just compute what the Laplacian of v is. So if I look at the double x derivative of v, well, I'm going to have to do, technically, I'm going to have to do the chain rule here, right? It's going to be the double x derivative of u. Sorry, let's just go back to one derivative. Oh no, wrong eraser. The x derivative of v is equal to the partial derivative of u, x plus a, y plus b, times the derivative of x plus a with respect to x, which is just 1. And so you can see that similarly, you're going to get the double x derivative of v is going to be equal to the double x derivative of u of x plus a, y plus b. And similarly, the computation will show the double y derivative of v is equal to the double y derivative of u of x plus a, y plus b. So then the Laplacian of u of x plus a, y plus b, this then is also going to be equal to 0. Like the Laplacian of this function is equal to the Laplacian of u evaluated at the same spot. So, in other words, if I write it in terms of v again, this would be the Laplacian of v is equal to the Laplacian of u at x plus a, y plus b. Okay, in other words, I'm doing the same differentiation, but just evaluating it at a different point. Okay, what about dilations? So dilations we need to be a little more careful with on what exactly we mean by in rotation invariance. We mean that this equation, or sorry, by what we mean by invariant, I mean this equation is invariant under dilations. So dilations, okay, this blue marker is not doing its thing for me, so I will switch. Dilations okay, these take a point, xy, and it just scales it by some non-zero number. So AB goes to the point lambda A, lambda B. I meant to write x and y. I don't know why I wrote A and B. Same thing. It sends the point AB to the point lambda A, lambda B. Just so that I keep things consistent, let me write this as xy goes to lambda x, lambda y, and then so v of xy is equal to, man, I need a break, is equal to u of lambda x, lambda y, and show, as an exercise, show that the Laplacian of v, show that the Laplacian of v of xy is equal to lambda squared times the Laplacian of u, lambda x, lambda y. Okay, so now the next thing that I want to look at are going to be invariant under rotations. And this is what I'm asking you to show. This is what I'm asking you to show in the homework. Okay, it's going to show the equation is invariant under rotations, and it's going to be invariant in this same sense here that I'll talk about in just a moment, or right now. So rotations are also a linear transformation, where it takes a vector in R2 and it rotates it theta degrees, or theta radians. So we have this vector that's getting rotated to that vector there. Okay, and so the formula for these transformations are pretty easy. The formula for rotation is a little more complicated. But the matrix for this transformation is given by cosine theta, sine theta, minus sine theta, cosine theta. And if I multiply it by a point xy in the xy plane, what you get is x cosine theta minus y sine theta, and down here you have x sine theta plus y cosine theta. And so, using the notation that I've been using above, xy gets mapped to this point. So for a rotation of theta radians, we have the point xy, running out of room a little bit, we have the point, let me write it down here. We have the point xy, this is getting mapped to this point. X cosine theta minus y sine theta, and then x sine theta plus y cosine theta. Okay, and now what I'm saying is if u satisfies Laplace's equation and v is defined as u, but at these points here, so if v of xy is equal to u, okay, so I'm going to have to do this ugly. It's going to be u evaluated at this point, x cosine theta minus y sine theta. That's the first argument. And then the second argument is going to be x sine theta plus y cosine theta. If v satisfies this equation, then the Laplacian of v is equal to 0 as well. So we say that the equation, we say that the Laplacian is invariant under these rotations. And the Laplace equation is invariant under these rotations. Okay, that's what we mean by that. Okay, and again, you're going to show this. How are you going to show this? Well, there's two ways. The most straightforward way is also probably the most tedious way, and you're just going, which is how I really honestly would suggest doing it, because I think it's good practice using the chain rule. So what you're going to do is just literally compute the second derivative of v with respect to x, the second derivative of v with respect to y, add them together and show that they're 0. And of course, for all of these, you're going to have to use the fact that the Laplacian of u is also equal to 0. The other way to show this is using the converse of the mean value property. That's all I will say about it. If you want to talk more about it, we can talk in office hours. Okay, so given the sort of the structural regularity of the Laplacian, meaning it's invariant, mostly meaning that it's invariant under rotations, then it makes sense that perhaps we can find a solution that is also invariant under rotations. I mean, it makes sense that the solutions to the problem should have the same sort of properties as the equation itself. Okay, so what do I mean when I say a solution that is invariant under rotations? Well, I mean it's just going to be a function of the distance of, so u of xy then is just going to be a function of the distance of the point from the origin. So I'm going to say u of xy is just going to be a function of x squared plus y squared, because x squared plus y squared is the square of the distance of the point xy to the origin. So I'm going to assume I can write this I can find a function f such that u of xy is equal to f of x squared plus y squared, and the Laplacian of u is equal to 0. Okay, so again, I just want to explain a little bit more about what I'm talking about. So when I say it's invariant under rotations, so notice the only information that f is being fed about the point x and y is the point's distance from the origin. So if this is my point xy, this right here, the distance from there to there is the square root of x squared plus y squared. Okay, so the only information that f gets about the points x and y is about its distance from the origin. So if I apply my u to this point or to this point, it's going to be the same because x squared plus y squared for this point is the same as x squared plus y squared for that point. Okay, so now what I'm going to do, actually I'm not going to do it, but I'm going to let you guys do this as an exercise because again, it'll be good practice with the chain rule, which is always kind of a tricky thing to apply, or it can oftentimes in this class, be a tricky thing to apply. I want you to show that the Laplacian of u, if u is defined this way, the Laplacian of u is equal to 4 times f prime of x squared plus y squared plus 4 times x squared plus y squared f double prime of x squared plus y squared. Okay, and I'm going to let r equal x squared plus y squared. And if I want the Laplacian of u to be equal to 0, I have that. So I have 0 over here. Both of these terms have a 4, so I'm going to divide by the 4. And I get 0 is equal to f prime of r plus r f double prime of r. Okay, now this is looking good because this is now an ordinary differential equation. So I can write this in the following way. I can write this as f double prime of r over f prime of r is equal to minus 1 over r. Okay, but this is just equal to the derivative of the log of f prime. So this equation, like I can rewrite this part as the derivative with respect to r of the natural log of f prime. Okay, so why is that? Well, if I look at this and I do the derivative using chain rule, I'm going to get 1 over f prime times f double prime, which is exactly what I have here. Now I can solve this equation for f prime of r, and it gives me f prime of r is going to be equal to some constant divided by r. I'll let you do that on your own. It's an ordinary differential equation, but the thing we're solving for now is f prime. We're not solving this, like going from here to here, we're solving this ODE for f prime, not for f. But now we're going to solve this for f prime. But we're not really solving anything, we're just anti-differentiating or integrating both sides. And what we get is f of r is equal to a times the natural log of r plus some constant b. Okay, and so this motivates the following definition. This motivates the following definition. The fundamental solution for the Laplacian is phi of xy. I need to make sure that I get this constant right. Is equal to minus 1 over 4 pi natural log of x squared plus y squared. So in other words, if I compare this to this, I'm taking b equals 0 and a equals minus 1 over 4 pi. So we're not going to be able to talk about it a whole lot, but there's a reason for this. There's a reason for it, and I'll touch on it in just a minute. Okay, so this is the fundamental solution for Laplace's equation. Okay, now, obviously, if we have something called the fundamental solution for Laplace's equation, well, the thing that was called the fundamental solution for the heat equation allowed us to solve the heat equation. So it seems like maybe the fundamental solution for Laplace's equation should help us solve the Laplace's equation. In other words, it seems like the function u of xy, defined as the integral over R2, and I'm going to use a and b as my variables of integration. So I'm going to have something like this. It seems like this should give us a harmonic function. Oh, sorry, this is not, this should be f. It seems like this should give us a harmonic function, and maybe f is involved somehow. But f being involved somehow is kind of tricky. How exactly is f involved? So the question is, what does u satisfy? So I'm going to write something that's wrong. I'm about to write something that's wrong. So what is wrong? So it's always very, very dangerous to write something that is wrong on the board. So I'm going to write everything that's wrong. Everything in this box that I'm going to write is going to be wrong, or it's leading to a wrong conclusion or something. It's going to be wrong, and then I'm going to tell you what the right thing is. So let's say I just naively try to compute the Laplacian of u. Well, the Laplacian is only happening in the x and y variables. So we've been doing this all through our entire semester so far. We've just been moving this inside the integral. The integral is in terms of a and b. The boundary is over all of R2, so the boundary definitely doesn't depend on x and y. So we would want to write this as f of ab times the Laplacian of phi x minus a y minus b dA. Okay, so technically we'd have to do the chain rule here, but notice the derivative of x minus a with respect to x is 1, and the derivative of y minus b with respect to y is 1, so this is okay here. And we just saw over here that functions of this form satisfy the Laplacian of u is equal to 0. We just saw, basically, that the Laplacian of this function is equal to 0. So it should say this is equal to 0, and now this is going to be equal to 0. Okay, so this is not right. Why is it not right? Well, let's come back over here. So it's definitely true that if I take the Laplacian of this, I'm going to get 0 as long as x and y are not both 0. If I try to do this at the origin, if I take the second derivative at the origin, I run into problems because I have a singularity. So what I get here is not, so this is wrong. So this is wrong. In fact, this is the wrong step here. Well, even this is also kind of the wrong step. They're both wrong. It just depends on what your interpretation of things are. So this is not true. Okay, so now I'm going to write what's right. What's correct is the following. If I look at this function here, what I get now is the Laplacian of u is equal to f of xy, but it's not quite that, the Laplacian of u. The Laplacian of u, the minus the Laplacian of u, defined this way, is equal to xy. Or if I just don't have the minus sign there, it would be Laplacian. If I forget about the minus sign in the fundamental solution, I can do it without the minus sign there. Okay, so then what we have then is the Laplacian of phi. This is equal to 0 if xy is not equal to 0, 0. So, sorry, minus the Laplacian of phi is equal to 0 if xy is not equal to 0, 0. And it's equal to the Dirac delta if xy is equal to 0, 0. Okay, so what do I mean by that? And of course, this means in the sense of distributions. So what do I mean? U of xy, sorry, if I have u defined this way and I take the Laplacian, or minus the Laplacian, I'm going to put this on the inside of the integral now. So it's going to be R2 we're going to have f of AB, and I'm going to do minus Laplacian of phi of x minus a, y minus b dA. Okay, so if the Laplacian of phi, if minus the Laplacian of the fundamental solution is equal to the delta, I've just translated it. So this now is going to be equal to the integral over R2 times the delta function, but now it's going to be centered at the point AB, or the delta distribution, the delta naught function, centered at the point AB, or sorry, xy. Okay, and the two-dimensional delta distribution is similar to the one-dimensional. It's just going to evaluate f at the point that it's centered at. And so this is going to be equal to f of xy. Okay, so associated to this, we have one other PDE that we're going to talk about, and it's called Poisson's equation. Look in the book for a derivation of Poisson's equation in a certain situation. Both Laplace's equation and Poisson's equation come up in a variety of situations. So whether we're looking, so there's not just one derivation. There's many times where whatever you're modeling will end up being a Laplace equation or a Poisson equation. But Poisson's equation is minus Laplacian of u is equal to f, or some people just write it as Laplacian of u is equal to f. But this is Poisson's equation, where we're doing the Laplacian of u is not equal to 0, it's equal to some prescribed f. So f is given here. And you can also talk about, you can also talk about Poisson's equation on a domain and Dirichlet problems and Neumann problems and things like that. Okay, so this video, I believe, has gone on long enough. Yes, so I've gone through a few questions here. So in other words, using the fundamental solution for the Laplacian, we cannot directly use that to solve Laplace's equation. I'm going to show in the next video how we can kind of come up with something that seems like it should be called the fundamental solution for the Laplacian, but only for the upper half plane. And I'll say more about what that means in the next video.